The ground you're standing on right now remains one of the greatest mysteries in the known universe. And in a remote corner of a Chinese desert, a team of engineers just spent 580 days trying to solve it. They drilled a hole almost 11 kilometers straight down into the earth. What they pulled out at the bottom wasn't supposed to exist. So, let's dive in. This is a photograph taken from the center of the Taklamakan Desert in northwestern China. It's one of the largest deserts in the world, flanked on every side by the Tian Shan and Kunlun mountain ranges. And for hundreds of years, nothing really happened here. But in May of 2023, a convoy of trucks rolled out across the sand, hauling over 2,000 tons of steel. They were carrying the single heaviest land-based drilling rig ever built. And this is the first look at what they came to do. It's called Shenditake 1, a vertical hole in the ground that would eventually reach a depth of 10,910 meters, nearly 7 miles straight down. To put that in perspective, Mount Everest is 8,848 meters tall. If you flipped Everest upside down and dropped it into this well, the peak would still be more than 2 kilometers short of touching the bottom, and that's not even the craziest part. But to understand why this hole matters, you first need to understand just how little we actually know about the planet we live on. Here's the uncomfortable truth. You already know the basic story: crust, mantle, outer core, inner core. It gets repeated in every classroom. But here's the thing. Almost all of it comes from inference, not observation. We've never actually seen any of it. The deepest anyone has ever drilled is a hole in Russia called the Kola Superdeep Borehole, which reached 12,262 meters. Kola was a Soviet project that began in 1970, originally meant to go 15 kilometers deep. Scientists had clear predictions. Seismic data showed that around 7 kilometers down, something should change, most likely the transition from granite to basalt. So when the drill finally passed that mark, everyone expected basalt. Instead, they found more granite. The expected layer just didn't exist. It turned out that the boundaries we see on seismic maps aren't always boundaries between different kinds of rock. Sometimes they're just the same rock, squeezed and fractured into a new structure, and it only got weirder from there. At 3 to 6 kilometers down, the drill passed through solid granite that was supposed to be bone dry. Instead, they found mineralized water trapped inside the rock itself. The drilling mud coming back up was described as boiling with hydrogen gas. At 6 kilometers, they pulled up core samples containing microscopic plankton fossils from an ancient ocean buried hundreds of millions of years ago. By the time they reached 12 kilometers, temperatures had climbed to 180 degrees Celsius, far hotter than the models predicted. The rock became soft and unstable. The drill string kept breaking. And in 1995, they ran out of money and closed the site. Kola never hit its target depth, but it proved something more important. We had no idea what was really going on beneath our feet. Fast forward 3 decades, China decides it's time to try again, but this time with a very different strategy. By the end of 2024, Chinese engineers had already drilled 191 separate wells deeper than 8,000 meters in this region, more than 300 wells in total. On May 30, 2023, drilling began. The goal was ambitious: reach a designed depth of 11,100 meters, pass through 12 separate geological formations, pull out core samples from rock that hadn't seen sunlight in over 500 million years, and along the way, build the technology that would one day let China drill even deeper. The rig itself was a monster. Called the 12,000-meter automated drilling rig, it was the first of its kind ever built anywhere in the world. For the first 8,000 meters, things moved at a reasonable pace. It took about 5 months. The drill bits chewed through layer after layer of sedimentary rock, each one representing a different moment in the Earth's history. Then, from 8,000 to 10,000 meters, the pace slowed. That next 2 kilometers took another 4 months. And then came the final stretch, the last 910 meters, the last kilometer. This is where things got strange. Going from the 10,000-meter mark to the bottom of the hole took more than 300 days, half of the entire project, half a year and a half of continuous drilling, just to advance the final kilometer. Why? Because the deeper you go, the more every law of nature begins to conspire against you. Let's break down what's actually happening down there. At 10,000 meters below the surface, the temperature climbs to over 210 degrees Celsius. That's hot enough to instantly vaporize cooking oil. It's hotter than most industrial ovens. And it never stops. The heat just keeps building up as you go deeper, because this kind of temperature isn't caused by fire or magma, it's caused by compression. The immense weight of all the rock above is squeezing the molecules of the Earth together, concentrating their energy, generating heat that has nowhere to escape. Alongside the heat comes the pressure. Above 10 kilometers, the pressure inside the well exceeds 145 megapascals. That's a hard number to visualize, so here's a better way to think about it. The deepest point in the ocean is the Mariana Trench. At the bottom, the pressure is so extreme that it would collapse a standard submarine into a sheet of foil. The pressure inside Shenditake, one at its maximum depth, is greater than the pressure at the bottom of the Mariana Trench. And you're not underwater, you're inside solid rock. Now imagine trying to operate a drill in that environment. The drill string connecting the bit to the surface is made of over 1,130 steel pipes threaded together, weighing more than 350 tons in total. The thinnest of them are only as thick as the lip of a coffee cup. At those temperatures and pressures, the steel itself begins to lose its strength. The lead engineer described the pipes as becoming soft, like cooked noodles, and the rock itself wasn't making things any easier. The drill had to punch through 12 completely different geological formations, each with its own hardness. Over the course of the project, more than 20 drill bits were consumed. The team had to invent a new kind of ultra-high temperature drilling fluid just to keep the equipment from cooking itself. For most of the problems they ran into, there was no reference data. Nobody had ever been this deep with this kind of equipment. They were writing the rule book as they went. But on September 27, 2024, a core sample was pulled up from a depth of 10,041.5 meters. A geologist named Tan Junping was the first person to touch it. The rock was grey dolomite, and it was still warm. Around 50 degrees Celsius of residual heat radiating out of it, carried up from the interior of the Earth itself. That single piece of rock was more than 540 million years old. It came from a period in the planet's history called the Cambrian, a time before dinosaurs, before fish, before even the earliest forests, when life on Earth was still mostly made up of strange, soft-bodied creatures swimming in warm, ancient oceans. For the first time in history, a human being was holding a sample of Cambrian rock pulled directly from that depth in Asia. It was like reaching back in time, but the rocks were just the beginning. As the drill continued to grind forward through that final kilometer, the team began to notice something strange in the readings coming back from the bottom of the well. Hydrocarbons. Traces of oil and gas appearing at depths for more than a century. The official theory of how petroleum forms has been based on the idea of a thermal window. Oil forms from ancient organic matter, like dead plankton and algae, that gets buried and compressed over millions of years. Under the right conditions of heat and pressure, it slowly transforms into crude oil. But if you heat that organic material up too much, it breaks down. It stops being oil. The molecules fall apart. The classical model says that anywhere below about 8,000 meters, the temperature becomes too high for oil to survive. It should be destroyed. There should be nothing left except methane gas at best, and eventually not even that. That theory is written into every petroleum geology textbook. It's the foundation of how we explore for oil and gas all over the world, and it was completely wrong. Between the depths of 10,851 and 10,910 meters, the deepest sections of Shenditake 1, the team discovered an active, producing reservoir of oil and gas, not just traces, not just faint indications. High-quality source rock, pumping out commercial-grade hydrocarbons from conditions that should have destroyed them millions of years ago. This was the first discovery of oil and gas below 10,000 meters on land anywhere in the history of the planet. It shouldn't have been there, and yet it was. So, what does that mean? It means that somewhere in our understanding of how oil forms, something fundamental has been missing. The classical thermal window theory assumed that the only thing that matters is temperature, but it turns out that other things matter too. Pressure matters. Water chemistry matters. The minerals in the surrounding rock can act as natural catalysts, slowing or speeding up the breakdown of hydrocarbons in ways that nobody fully accounted for. Under extreme pressure, the very chemistry of how molecules hold together begins to change. Carbon-hydrogen bonds that should break don't. Methane that should evaporate or react just sits there, stable and preserved, waiting for someone to drill down and find it. And this discovery doesn't just rewrite one chapter of geology, it rewrites the entire map. If oil and gas can exist beneath 10 kilometers, then every major sedimentary basin in the world has a hidden layer that nobody has ever explored. In the Tarim Basin alone, Chinese scientists now estimate that the ultra-deep hydrocarbon potential could be over 6.6 trillion cubic meters of gas, spread across an area of roughly 120,000 square kilometers. For context, that's more than twice the size of Belgium, and it's just one basin. There are similar ancient basins in Siberia, in the Middle East, in North America, in Africa, all of which may be hiding resources at depths that nobody has ever bothered to look at because nobody believed they could be there. But this is just the energy side of the story. The real scientific discoveries are still down in the rock itself. Remember how the Kola borehole found water and hydrogen in places they weren't supposed to exist? Shenditake 1 is confirming that same pattern on a much larger scale. At these depths, the Earth's crust is not dry. It is not sealed. It is not an impenetrable wall of solid rock. Instead, it's a living chemical system. Fluids are moving through it. Reactions are happening inside it. The rock is fractured along fault lines and shear zones, and those fractures let water, gas, and dissolved minerals circulate through environments that should be far too hostile for anything to move. In ultra-deep wells around the world, scientists are now finding high concentrations of hydrogen gas being generated naturally, several kilometers below the surface. Some of it comes from a process called serpentinization, where water reacts with iron-rich minerals like olivine to produce hydrogen as a byproduct. Some of it comes from radiation. The natural decay of uranium, thorium, and potassium atoms in the deep crust splits water molecules and releases hydrogen over hundreds of millions of years. And some of it may come from a third source we are only just beginning to understand. Thermogenic hydrogen, produced when ancient organic matter is cooked beyond the point where it can form any more oil or gas, eventually releasing pure hydrogen as its final product. Taken together, these processes suggest that the deep crust of the Earth might be one of the largest hydrogen factories on the planet. And hydrogen, of course, is one of the most important clean fuels of the future. If we can figure out how to safely tap into these natural reserves, we might unlock an entirely new kind of energy resource that doesn't require burning anything, that doesn't produce carbon dioxide. That just sits down there, quietly being generated by the Earth itself, waiting for us to come find it. This is what they mean when they say Shenditake 1 is not just an engineering achievement. It's a scientific revolution, and it keeps going. At these depths, the Earth's interior also becomes a giant natural laboratory for understanding how earthquakes happen. The brittle upper crust, the part that cracks and breaks and generates tremors, is supposed to give way to a softer, more ductile lower crust, somewhere around 10 to 15 kilometers down. But direct measurements from ultra-deep wells suggest the actual transition is deeper, more variable, and more strongly influenced by fluids than anyone realized. In Germany, an earlier ultra-deep project called the KTB borehole ran experiments where they injected small amounts of fluid into the deep crust and then monitored the result. They found that even tiny pressure changes, less than 1 megapascal, were enough to trigger hundreds of micro-earthquakes, kilometers below the surface. That's an extraordinary finding. It means the deep crust is critically stressed. It's like a string pulled so tight that the slightest touch can make it vibrate. All those earthquakes we experience on the surface, they might be controlled by conditions far deeper than we ever imagined. By understanding what's actually happening down there, projects like Shenditake 1 could give us a fundamentally better picture of how and why major earthquakes occur and potentially help us predict them. It could also help us harness geothermal energy in places we never thought possible. Right now, most geothermal power plants rely on finding naturally occurring hot springs or shallow volcanic systems. But if you can drill deep enough, the heat is everywhere. At the depth Shenditake 1 reached, the temperature is hotter than a pizza oven, and that heat is available underneath almost every continent on Earth. If drilling technology continues to improve, we might one day be able to put a geothermal plant anywhere we want. No volcanoes required, just a long, narrow hole reaching down into the warmth of the planet itself. The implications for the global energy transition are enormous. But for that to happen, the engineering has to keep getting better, which brings us back to the drill itself and to the machine that made all of this possible. The rig that drilled Shenditake 1 was not just impressive. It was a prototype for the next generation of deep Earth exploration. The automated drilling system on site was monitored and controlled from a command center in the city of Kola, hundreds of kilometers away. Engineers watched real-time data streaming up from sensors embedded in the drill string, adjusting the speed, the torque, the pressure, the flow of drilling fluid, all remotely. They developed specialized drilling muds designed to withstand extreme temperatures without breaking down. They created new casings and cements that could seal the walls of the well, even as the surrounding rock tried to collapse inward. And they did all of this in a remote desert, in one of the harshest environments on Earth, while fighting a series of problems that nobody had ever encountered before. It is, in its own way, as significant an engineering accomplishment as landing on the moon. And the Chinese scientists who led the project have been very clear about making that comparison. An academician with the Chinese Academy of Engineering described the challenge of drilling Shenditake 1 as being just as difficult as a lunar exploration mission. He wasn't exaggerating. In some ways, going deep is harder than going up. In space, there is a vacuum, and the biggest enemies are cold and radiation. Down here, there is no vacuum. There is rock and pressure and heat and chemistry, and every single meter the drill advances, the conditions get worse. There is no way to stop and turn around. There is no way to send a rescue mission if something goes wrong. The equipment is on a one-way journey into the unknown. But Shenditake 1 isn't the end of the road. It's the beginning. China has already announced plans for something even more ambitious. A new drilling project designed to reach a depth of 15 kilometers. That would make it the deepest borehole ever drilled on the planet, surpassing even the Kola Superdeep. To put this in perspective, at 15 kilometers down, the temperature is expected to climb to around 400 degrees Celsius. That's hotter than most home ovens can go on their highest setting. It's hot enough that conventional electronics simply stop working. hot enough that most drilling fluids break down completely, hot enough that the steel used in normal drill pipes begins to lose its structural integrity. At those depths and temperatures, the rock itself may behave in ways we've never seen before. The scientist leading the planning for this next project has warned that at 13,000 meters, the rocks are under so much stress that they may literally explode when the drill releases the pressure around them. That's not a metaphor. He's describing an actual phenomenon where the act of drilling causes nearby rock to violently fracture and shoot outward, potentially damaging or destroying the equipment. To handle conditions like that, Chinese engineers are now working on entirely new classes of materials, heat-resistant drilling fluids that can function at over 400 degrees, diamond-impregnated drill bits that can maintain their edge over hundreds of hours of continuous operation, automated drill string systems that can make precision adjustments thousands of meters below the surface. Some of the technologies being proposed sound almost like science fiction. Laser-based drilling, plasma cutting, downhole power generators that can create electricity at the bottom of the well where no cable could survive. The goal of all this is not just to break records. It's to transform deep earth exploration from an occasional engineering stunt into a routine scientific tool. Imagine a world where we can drill through the full thickness of the continental crust and actually sample the upper mantle. That's the layer of the Earth below the crust where convection currents drive plate tectonics, where volcanoes are born, where the slow churning of hot rock over billions of years shapes the surface of the entire planet. Nobody has ever touched the mantle. We've sampled it indirectly from volcanic eruptions and from pieces of rock pushed to the surface by tectonic forces. But we've never drilled down and collected a piece of it ourselves. Even Shenditake 1, at nearly 11 kilometers deep, is still far from reaching it. Below the continents, the crust is on average about 30 kilometers thick. Under mountain ranges, it can be as thick as 100 kilometers, so the journey is just beginning. But for the first time in human history, the tools needed to complete that journey are starting to exist. And once we finally do touch the mantle, when we finally pull up a core sample from that deep, the textbooks are going to get rewritten once again. In the meantime, the samples from Shenditake 1 are already reshaping what we thought we knew. The well has provided the first 10,000-meter deep core samples ever collected in Asia. Chinese scientists have used those samples to build the country's first comprehensive ultra-deep stratigraphic profile. A detailed, layer-by-layer map of the crust from the surface all the way down, showing exactly what kind of rock is present at each depth, how it formed, what chemicals it contains, and what it tells us about the ancient history of our planet. This kind of data is invaluable. It's the geological equivalent of a core sample from the polar ice caps, except instead of recording climate change over the last few 100,000 years, it's recording the evolution of the Earth over hundreds of millions of years. Everything that happened during those 500 million years, every shift of the continents, every rise and fall of ancient oceans, every mass extinction, is recorded in the layers of rock that Shenditake 1 passed through. And then there's one final thing, one last strange discovery that makes the whole project feel even more remarkable. When scientists modeled what they expected to find in the deepest layers, based on all the existing theories about how continental basins evolve, the results didn't match what the drill actually pulled up. The dolomite rocks at the bottom of the well showed signs of preserved porosity. That means there were still tiny pockets and channels inside the rock that had not been crushed shut by the overwhelming pressure from above. According to traditional theory, at the depth and pressure and temperature found down there, porosity should be essentially zero. The rock should be squeezed into a solid, impermeable mass. But it wasn't. Pockets remained. Fractures remained. Fluids were still moving through them. The rock at the bottom of Shenditake 1 was still alive in a geological sense, still active, still evolving, and nobody is entirely sure why. One theory is that early in the history of the rock, Before it was buried so deeply, certain chemical processes during its formation created a kind of structural scaffolding that kept the pores from collapsing even when the pressure increased. Another theory is that the constant flow of hot fluids through the rock has continuously dissolved and reprecipitated minerals, maintaining open channels in a kind of dynamic equilibrium. Whatever the explanation turns out to be, it means the traditional rules for how deep rocks behave are probably wrong, or at least incomplete. And so we come back to where we started, to that quiet spot in the middle of the Taklamakan Desert, where a group of engineers spent 580 days pushing the limits of what humans are capable of. They drilled a hole, just a hole, a narrow vertical shaft into the ground. It sounds so simple, but that hole has already revealed that oil can exist where it shouldn't. That hydrogen is being produced by the planet on a scale we're only beginning to understand. That the deep crust is wetter, more fractured, and more chemically active than anyone believed. That entire energy resources have been hiding underneath us the whole time, waiting for someone to go and look. And that's what makes Shenditake 1 so interesting. It's not just an achievement of engineering, it's a reminder of how little we know about the planet we live on. We have spent generations looking up at the stars, dreaming of what lies beyond, and we've made incredible progress. But the greatest unexplored frontier in the solar system might not be out there at all. It might be directly below your feet, right now, just waiting for someone to finally drill deep enough to find out what's really there. And eventually, we will.